This is the Homeschool Chemist, and today we're going to look at a problem where we are asked to find the grams of products at equilibrium given the grams of reactant and given Kc. So in this problem, they're asking us to consider the reaction of 2ICl going to form molecular iodine and molecular chlorine, or I2 and Cl2. We're given the Kc of 0.11, and we're asked if we start with 164.97 grams of iodine and 23.4 grams of chlorine, and we have a 1.5 liter vessel, how many grams of ICl will we have at equilibrium? So the first thing we need to do here is to go from grams to moles to molarity, because whenever we do an equilibrium problem, we need to know the concentration of everything, not the grams or the moles. So if we are starting with 164.97 grams of I2, and if we add up what the molecular mass of I2 is, we find that it is 253.8 grams per mole. And if we multiply that through, that comes out to be 0.65 moles of I2. Now we'll do the same for chlorine. We're starting with 23.4 grams of Cl2. From the periodic table, we can add up the mass of Cl2, which is going to be 70.9 grams per mole, which will come out to be 0.33 moles of Cl2. Now, we have our moles from our grams. Now we need to get to concentration in molarity. So if you recall the formula for molarity, molarity is equal to N, which is number of moles, over V, volume in liters. We're given our volume in liters here, 1.5 liters. So we're just going to divide each of these moles by 1.5 liters, and we are going to be left with 0.433 molar and 0.22 molar. Now that is our concentration. Now the next step is going to be to write what I like to call an icebox. It stands for initial change in equilibrium. So we're going to write our chemical reaction here, but I'm going to write it differently than it's given to us. And I'll explain why in a second. So I'm going to write I2 plus Cl2 is going to be in equilibrium with 2ICl. Now the reason I did this is because this particular problem, it gave us the Kc for the reaction going from ICl to I2Cl2. But what we're finding here is we're starting with what would be our products. Therefore, the reaction is going backwards, so our products are actually going to be our reactants. So I'm going to reverse the equation so we can read it from left to right. But if I'm going to reverse the equation, I need to find the Kc for the reverse equation. So Kc for a reverse equation is just equal to the inverse, or 1 divided by the Kc of the forward reaction. So in this case, our Kc reverse would just be 0.11 to the negative first power, or 1 divided by 0.11. So our new Kc for the reaction, the way I have it written, is equal to 9.09. Now I'm going to write my ice over here for initial change in equilibrium, and we were given our initial concentrations, which we solved for. So we started with 0.433 molar of I2, 0.22 molar of Cl2, and we started with 0 ICl. Now the change. we can see that it's going to be a 2-to-1 ratio between reactants and products. So for every 1 mole of reactant that we use up, we're going to get 2 moles of product. So over here it's going to be minus X, and then over here it's going to be plus 2X. And then for equilibrium, this is just going to be 2X, because 0 plus 2X is 2X. Over here is going to be 0.433 minus X and 0.22 minus X, because at equilibrium, the molarity of I2 and Cl2 is going to be our initial concentration minus our change. That's simple. So now we're ready to write a equilibrium expression. So Kc, which is a constant for a chemical reaction, is equal to the concentration of products over reactants. And each one is going to be raised to the power of its balancing coefficient. So what that's going to look like for us is the Kc of this particular reaction. Well, we have ICl as a product, because I changed the way the reaction was written. And we're making 2 of those. And this is a concentration, but we have to square it. For the bottom, we're going to have, at equilibrium, our concentrations of I2 and Cl2. Now, because the balancing coefficient for each of these is 1, any number raised to the first power is just itself. And this Kc is equal to 9.09. So using this, we can now set up a expression from what we had written on the previous page at our equilibrium to solve for our concentrations at equilibrium. So 9.09, which is Kc, is going to be equal to 2x squared over 0.433 minus x times 0.22 minus x. All right, and if you recall from the previous page, this is what we had written on the E part of the icebox. We had 2x over 0.33 minus x and 0.22 minus x. So the first thing I'm going to do is I'm going to FOIL the bottom. I'm going to multiply these together. So firsts, outsides, insides, lasts. And what that is going to give me is 9.09 is equal to x squared minus 0.653x plus 0.095, and that's going to be over 4x squared. Because the 2x is in parentheses, I have to square the 2 and the x. The next step is going to be to multiply the bottom of this out into our Kc, and that is going to give me 9.09x squared minus 5.94x plus 0.86 equals 4x squared. And you may be able to see in this case we're going to have to solve the quadratic for x, so we need to set this equal to 0. So I'm going to subtract 4x squared from both sides, which is going to give me now 5.09x squared minus 5.94x plus 0.86 is equal to 0. Now we can use the quadratic to solve for x. So if you remember, the quadratic formula is opposite of b plus or minus the square root of b squared minus 4ac, and the whole thing is over 2a. So if I were to go ahead and make this a, b, c, and I ran this through my calculator, I would get 2 values of x. I would get x is equal to 0.169 and x equal to 0.998. Now, only one of these is correct. we're going to reject the bottom one, and this is why. If I were to take 0.99 and come, let's say, over here in our previous page, look at equilibrium, 0.433 minus 0.998 is going to be a negative number. Likewise with 0.22 minus 0.998. You can't have negative concentrations. And also, you cannot make more products than you have reactants to make them with. That's just logic. So because of that, I'm going to reject the bottom one, and we're going to go with the 0.169. So I'm going to write the equation out once again. So we got write that differently. So we got I2 plus Cl2 is going to form ICl. We have our initial change equilibrium. We had 0.433 over here, and we had 0.22, and we had 0, and then we had plus 2, and we had x. So x is going to be, we found out x is 0.169. This one is 0.22 minus 0.169. 0.433 minus 0.169. And what that's going to give us for our equilibrium concentrations is that's going to give us 0.264, 0.051, and this is in molar, and it's going to give us 0.338 molar. Now, we have found our concentration at equilibrium of all the species. The problem, however, asked for the amount of ICl in grams. So if we recall, molarity is equal to N over V. If we rewrite this and do molarity times volume, that is going to be equal to the number of moles, which is what we're going to need to find here. So what that looks like for us is 0.338 molar times 1.5 liter, that was given to us in the problem, is going to equal 0.507 moles of ICl. So now we have the moles. Now we just multiply by the molar mass to get grams. So 0.507 moles of ICl. 1 mole, if we add up the molar mass of an iodine and a chlorine, we're going to find it's 162.35 grams. And if we multiply that through, we're going to find it is 82.3 grams of ICl. So in this particular problem, we went from grams of reactants. We had to reverse the equation and get the Kc reverse. Then we solved for x and found the concentration and molarity at equilibrium, which is right here. And then from there we could get moles and we could get grams. And so our final answer, if we perform this reaction in a 1.5 liter vessel, we would find that we would get 82.3 grams of ICl. Thank you for watching.